한국어로 손발이라고 해요. 손발에 참은 뭐 가리지. 그래서 제가 아주 저거를 세미나는 발표는 영어로 할 거예요. 용어를 몰라요. 근데 질문은 한국어로 해주셔도 돼요. 한국어로 해주셔도 되고, 한국어 영어로 해주셔도 되고, 한국어를 영어로 섞어도 되고, 그러면 저는 적당히 대답을 해주세요. 질문을 좀 많이 해주시면 됩니다. Can we talk about attention to quantum complexity? I think that's part of it. So this is we're trying to find the details of this work in the preprint, and there's delay가 있는 것 같아요. 아니 같이 여기서 보이세요? 이쪽 보이시죠?
예.
네, 그냥 이쪽 보고 하면 될 것 같아요. So I am a matter theorist by training. I've always been really interested in trying to understand how to connect what we observe through various experiments with theoretical insight. And in order to understand complex data with simple theoretical insight, what we always have to simplify somewhere. And the question is, as we try to compress the information that we observe from experiments, whether we are retaining the essential elements, and it's hard to know. So in order to verify that the theories that we are making has bearings in the experiment, I want to be able to go back and forth between the two. But as the volume of data grows and the modality of experiments become more richer and more complex, it's become harder and harder to be able to go back and forth. So for about 8 years now, I've been exploring how to leverage machine learning and data scientific tools to help us make these loops connect better. And recently, for this meeting for the last 3 years or so, I've sort of my group's research have expanded to include data from quantum simulators as part of this larger picture. So why should we try to use machine learning? What do I mean by data-driven challenges? So as scientists, the scientists for the last 100 years have been trying to obtain data. It's all about making measurements. How many of you are experimentalists? Okay. And how many of you are theorists? If you're either a theorist or experimentalist, maybe you could do both, right? So if you're an experimentalist, your mission is to obtain data, right? So for over 100 years, the pursuit has been to obtain data. You improve the facilities, you improve the instrumentation, you improve resolution. We care about resolution, we care about reducing noise. But I claim that now that we have really improved various ways of obtaining data, we are entering a kind of a new era where we need to really think hard about how can you turn data into value. So something that really illustrates that point is this experiment. Now, these two people are Stern and Gerlach, and you probably have learned Stern-Gerlach experiment when you first learned quantum mechanics. Through this experiment shown in the class, this is actually the data presented in their paper. They have shown that there is two-dimensional Hilbert space associated with spin half. And the way this was shown was to take the collection, each of the silver atoms that were either going up or down. Each of them will land either here or there, right? Each of these pixels are, or the dots in the data, a result of silver atom landing on that screen. Once it lands up, it cannot go down. Obvious, right? Now, this, when I learned quantum mechanics in my junior year, we just learned it as one of those experiments that established the foundation of quantum mechanics. But now that when we look at this experiment from today's perspective, modern perspective, we realize that this is humanity's very first projective measurement. That was 1922. So now we fast forward to 100 years to today. Instead of making those projective measurements to probe the Hilbert space of single qubit, we, with your 20 qubit or 40 qubit, whatever number of qubit system, you make projective measurements to probe the Hilbert space of 2 to the n dimensional Hilbert space of your qubits. And instead of having up or down, what you have is this many possibilities, 2 to the n possibilities, depending on when you project, whether each of your spin qubits will come out in 0 or 1, right? So here I'm showing, it doesn't look like much, but this is actual data. This is actual data of projective measurements on 36 qubit system, right? So when we get data from our collaborators, that's what it looks like. We have a collection of zeros and ones. And we get, if we have million bit strings, we call this bit strings because these are bits. If I just write it down, snake, that's a bit string. So we call those bit strings. And that's the data that we're looking at. Now you can average them all and say what is the magnetization, or you can look for some patterns and looking for patterns in the magnetization would be to look for classical information, linear intensity matrix information, expectation value information, order parameter information. That's all the same. All of the phrases that I use are exactly the same. And what it all amounts to is to take all this collection of data and compress it to one number. That's what the order parameter is. But if I actually keep track of how many times this particular bit string projected measurement shows up and how many times this particular bit string shows up, I can count them and make a histogram out of all the counts of each configuration that I'm observing. And the histogram is sampling from this distribution. Histogram samples from this probability distribution of all the bit string possibilities. When I have 1 qubit, there are only 2 possible states, and that's what Stern-Gerlach did. When I have 36 qubits, I have 2 to the 36 different possible states of the bit string arrangement. And depending on what kind of state that I have implemented on my hardware, I will find different distributions. For instance, if I have prepared my state to be all 1, and all the qubits are 1 in product state, right? 1, 1, 1, 1, 1 product state, and I do make the measurements in the Z basis, I would only find 1 line, and everything else should give me exactly 0 count. And no matter if I prepare that same state, no matter how many times I measure, I will see only 1 line in this one. On the other hand, if I prepare the GHZ state, superposition, equal superposition of all 0 and all 1, right? Then I should see 2 columns. So these kind of counts would tell me what kind of state I have prepared. Problem is, I don't get to know the density matrix itself. What I would know what I intended to prepare, but whether that is exactly what the hardware have realized is not something that I can tell directly. But all I can access are these measurements, projected measurements. So just like Stern and Gerlach had to puzzle their way backwards from their first measurement, figuring out like, oh, if I first go through Z and then I go through X, I see something different from first going through X and then Z. There is a whole series of experiments that, when you first learn quantum mechanics, you learn how to reconstruct from those outcomes what state the system is in. That effort, that task of going from measurement to figuring out what state you have is a non-trivial reverse problem. So now what we figured out, that what I want to talk about today, my title of the talk says Attention to Quantum Complexity. And I've given this talk a couple of times, and I get various feedback from old friends, new friends. I come from condensed matter background, so I still work on solid state materials and solid state phenomena. And my friends who are doing, let's say, STM or transport or ARPES would say that, I couldn't figure out what is the data that you're looking at, and this is all very unfamiliar to me. And then I talked to people who are working in the quantum science, quantum computing. They say this whole machine learning thing, flew by, and it was all unfamiliar. So one thing that I do want to accomplish is I want to convey two things that are coming together to make my title to everybody. The title was Attention to Quantum Complexity. So I want to convey what attention is. Of course, you all know you're supposed to pay attention when somebody's giving a talk instead of falling asleep, but it's not attention in that sense. It's a specific technical term in the machine learning sense. Quantum complexity is also the word quantum is something that you hear a lot. Complexity is something that you hear a lot, but quantum complexity has also a technical. So I want to convey what attention is and what quantum complexity is and why trying to use attention mechanism to learn quantum complexity makes sense. Why we were successful. So let me start with attention. But the problem, largely speaking, that I'm interested in is how can I characterize and certify the state that's been realized in a quantum project. So what is attention? So here's an example of a sentence. He lives in the White House. Now, when you use language models like ChatGPT, the sentences that you type in is treated as a vector. So I am considering this as a vector of length 6. There are 6 entries to the vector. And each word are elements of that vector. The whole thing about the language is a sentence, understanding a sentence. No matter how well you understand a given word, you can understand the word white to mean a specific color. You can understand the word house to mean a specific structure of a building. But understanding white and house separately does not help you understand what White House means together. White House means something very specific, which is different from greenhouse or yellow house, right? In order to understand what a White House means, you have to bring the two words together. You have to think about the words in combination. But once you think about the word white and house together, you immediately understand who he is. Because the fact that the White House means a specific building gives immediate has an immediate implication on who he is. That means you want to think about these two elements of your vector together, and also this element together, which is kind of far away in the structure of a sentence. So when people were working on the whole research on language model that goes back pretty far. The challenge always have been that we have a sequence of words and we need to somehow think about different words together. We have to correlate the words. That's always been known. That was known as a challenge. That's the data challenge. And there were various attempts to tackle that bottleneck issue so that you can do machine translation or generation of response or understand natural languages. The technique that the mechanism that became known in this paper that really transformed how we can interact with the language learning model is this the mechanism called attention mechanism. And it's a relatively simple idea. The idea, until this idea came about, people were trying to build in correlations by looking nearest neighbors and next nearest neighbor, and every now and then little farther neighbor, right? But a sentence can be very long, and how far you have to go to get something meaningful depends on a grammatical structure of a different language. What these people did in this paper was to say, well, instead of trying to just build manually nearest neighbor and every now and then further neighbor, every now and then little farther neighbor, and every now and then retaining some amount of memory, let's take the whole sentence and just rotate that vector. So you rotate with one matrix called query and another matrix called key. You take the given vector, rotate it twice, and it's a little bit like Rubik's Cube. When you rotate it just right, they will click. So when you rotate the vector, you can make sure that the elements that you want to think together come to the same position and therefore give you a high score in this attention score. So this attention, self-attention, this attention score is a key element of attention mechanism, and then it gets exponentiated to give nonlinearity and so on. But the key thing that you learn in this, when you train a model, you're learning this K and Q2 matrices. Those are what is learned, and what the model is learning is that these are this is the correlation that you want to make together. So we started in my group, we started thinking about attention mechanism as a versatile way of treating correlation between different pieces of my data. We started to tackle this question of how can we learn about the characteristic of the data. The first attempt was to do generative modeling. We initially thought, well, let's take enough data so that we can reconstruct the full probability distribution. So this full probability distribution it amounts to looking at the diagonal entries of the density matrix. It's not even reconstructing the full density matrix, but if you have enough of this, and if you take more measurements in multiple axes, you can try to even reconstruct the density matrix. So initially, we tried to reconstruct the density matrix in this paper. And given the limited time, let me just kind of move fast because this was not the most successful attempt. So the idea was to take this transformer. This transformer is a name that's called for this mechanism, the large language model element that uses the attention mechanism. And we took the transformer architecture literally from that paper, that's Swami's paper, and took half of that, because the code is all available open source, and we fed it with the data, positive operator value measurement data, and try to reconstruct the density. And reconstructing density matrix from measurement is called tomography in the quantum computing in the field. So this is really trying to do tomography. Now, if you know anything about tomography, you know that it becomes harder and harder as your system size gets bigger because of the exponential challenge. And we were wondering whether the amazing power of the attention mechanism would somehow magically solve that exponential problem. Although our attention-based tomography required much fewer data for reconstruction of density matrix compared to another machine learning-based model, and we could, reproduce the density matrix just as well as MLE tomography. This was done on IBM's IBM Q machine back in the day. When was it? 2019. And so left-hand side is the result of MLE. That's sort of a manual approach, traditional approach of reconstructing the density matrix. These are reverse problems, so you're optimizing with it. And the right-hand side is attention-based reconstruction. You can see that they are similar, but this is just for 3 qubits. And although we could do just as well as the conventional approach for 3 qubits, and we could push to 6 qubits, but really what we couldn't break was the exponential wall. That is, as we got to larger and larger systems, we just needed unrealistically large volume of data. And that's when several very obvious realities hit us. First of all, exponential problems are big hard problems. And second, perhaps more importantly, the life lesson is there's no free lunch, there's no magic. You cannot try to take something and just hope that it would magically work. Life doesn't work that way. So did we give up? No, we decided that let's try to attack this from a different angle. So this sort of blindly hoping that it will somehow work didn't work. So let's try to look at a new problem where we can actually have success and make sure that we approach this in a systematic way. And that's our take two. That's in this preview. So how did we rethink, regroup ourselves? We thought, okay, let's first figure out what we should learn, what we should try to learn, because trying to reconstruct the full probability distribution seemed to be an unrealistic goal, not attainable. We wanted something that can be achieved with finite amount of data. So we have to change the target. If you can go, if I can climb Everest, I don't think I will ever climb Everest in my life, but I can try to climb something else, right? Something else that has to be still meaningful. So the new goal that we formed was the notion of quantum complexity, which I will define what it is. And then the next thing is, how will we learn quantum complexity? We will still use attention, but we are going to use attention between the snapshots. So then what were we doing before? Before we were trying to learn structure in the space of qubits. That was a spatial structure correlation. But we realized another very obvious thing once you sit down and think about it, the quantum mechanics is a theory of dynamics. Quantumness is about time evolution and time fluctuation. So if I want to learn sort of quantumness from the data, I really want to learn the fluctuation from shot to shot, not the structure inside the arrangement of qubits. So that's our new goal, and this time we approach this much more systematic. So quantum complexity, what is quantum complexity? I promised, well, I didn't promise, but I have my ambition for this talk that I want to convey what attention mechanism is, and I want to convey what relative quantum complexity is. So let's do that. Let's say I have two states, alpha and beta. If they are pure state, I would write as ket alpha and ket beta. If I have these states in the Hilbert space, which is the vector space these states are defined in, I should be able to define distance between the two states. I want to be able to say, so you see that I'm kind of changing my target from trying to understand one state in its entirety, from just being able to compare two states, right? From generated modeling perspective, it is, or machine learning perspective, it is, instead of wanting to be able to draw a path, I want to be able to at least say cats are different from dogs. Obviously, distinguishing is a lower level task than being able to know the full picture of an object. To know the full picture of the object here defined as a state is going to take way too much data. If we are working with 100,000 qubits, it's just not feasible. But if I have realized a state on a 100 qubit quantum computer, I want to know, is it what I intended? Is it, if I have some error correction code, I want to know whether the logical error occurred. I want to be able to answer multiple choice questions about my state. And one of them, one way to phrase it would be, I want to be able to tell how different one state is from another. Now, if I think about a space and two objects in that space as a point in that space, I would say, well, I have one state here and one state there. The relative difference, how different they are, will be a notion of distance between the two states. So the first thing that one might think of is, if I have two wave functions or two states, I might want to know, I might ask what their overlap is. So overlap is an obvious one sort of a very natural choice that people do. This notion of quantum complexity was raised as people started to ask questions about quantum chaos and wanting to understand information theoretic perspective on black holes. So black holes are something that objects that suck in everything. Radiation cannot escape black holes. So then people who are studying black holes started to ask, what is the quantum theory of black hole? That's the quantum gravity. And if I can develop a quantum theory of black hole, how do I think about information being able to escape or not escape? So this notion of looking at the distance between states sort of brought several different fields together: quantum gravity, information theory, and quantum chaos, and thermalization. These different pursuits came together into that one concept of wanting to understand the distance between the states. And if you think about this from the time evolution perspective, the inner product between state alpha and state beta is not going to change if I evolve both states under the same Hamiltonian, because it's going to be minus IHT on alpha, and it's going to be minus e to the IHT on beta. So this is equal to each other, right? So inner product is not something that will evolve under time evolution. It's not going to be a measure that you can use to define distance that's growing as you evolve under chaotic Hamiltonian. No matter how chaotic the Hamiltonian is, it is giving you a unitary evolution, because it is unitary evolution would move the two states the same way. It's not going to give you a notion of distance. But if you know the classical chaos, you talk about Lyapunov exponent, which is about how the trajectory diverge. So in order to think about chaos, you need to be able to define the distance in a way that inner product wouldn't work. So what people realize is that you can think about a state complexity by saying that, okay, what is the shortest minimum circuit depth that I have to apply to a given simple state in order to get to this state. So if I were to give some measure of complexity to a state size, you define that by saying, let's find unitary that the circuits that will evolve the simple state, like a product state, to this given state, and find the shortest depth such unitary to define complexity. If I am given two states, I can either try to define the complexity from evolving from a reference state, or I can try to define complexity, relative complexity between the two states by saying what is shortest depth unitary to evolve this state into that state. States are vectors in a space. You should be able to go from one to the other. You can transform. That's what you can do with vectors. So there would be different unitaries. You can build up, if you know how to get to alpha and how to get to beta, you can obviously go from alpha to beta by first reversing how you got to alpha by going back to zero, and then from zero to beta. But the complexity of a state is defined by the minimum circuit depth. So this notion, this concept was theoretically natural and appealing, but it is impossible to evaluate. So it's not practical. Nobody can actually take this concept and use it. What we decided to do was, instead of we will develop a stand-in for relative quantum complexity that's comparing the two states by turning it into recognizing this is a distinguishing problem or classification problem, and we try to learn this difference between states by using a mechanism, a machine learning mechanism, that can learn the salient features of the state. Now, then comes the challenge of what machine learning architecture we should use and what we should try to learn. Something that was important for us is to realize that in order to tell the evolution of states, you want to learn the moments of the distribution. This is another thing that is kind of a challenge, sort of a, how to put it, a stumbling block for people to follow this whole story. People are used to thinking about moments of the operators, we all know the first moment of the operator is expectation value. You also know correlation functions, right? 2-point functions. And when we think about correlation functions, we think about correlation function of the operator. But here, I am taking a very different perspective. I want to learn something about state, not using operators. I want to learn something about state that is agnostic to what operator I use. I want to learn about the distribution of the bit string. So if I want to know the structure of the bit string distribution in that probability distribution, and if I can't know all aspects of the distribution, I can at least try to know different moments of the distribution. We know that if I just need to know 2 moments, the lowest moment and the second moment, to fully specify Gaussian distribution. That's what's special about Gaussian distribution. Gaussian distribution is different from Lorentzian or some other distributions because the moments become different. So if I want to know how the 2 states are different, I would try to see if I can learn moments of the distribution, but without fully evaluating it, because full evaluation would be difficult. Now, these are formulas that say that for random circuits, if your time evolution is through random circuits, it is known that as you make the circuit deeper and deeper, what changes is the high moments. There is a theoretical grounding for wanting to learn moment. But for our purpose, for the purpose of this talk, it's sufficient to realize that I would be interested in trying to learn the moments of distribution as a stand-in as an approximate way to learn how the distribution itself is changing. Any questions at this point? All crystal clear? Can I quiz?
이 모멘트라는 게 무슨 뜻이에요?
이게 이 probability distribution이 있으면 그거를 그 probability distribution의 K power를 보겠다는 거예요. 네. 왜냐하면 그러니까 이게 그 distribution이 있으면 그 distribution의 flow shape은 모르더라도 first moment, second moment, third moment 그 모멘트를 알면 그러니까 probability distribution theory 그러니까 probability theory perspectiv인데 모멘트를 알면 두 디스트리뷰션이 다르다는 거를 디스트리뷰션을 완전히 리컨스트럭트 아니라도 알 수가 있다는 거죠. 네. 그래서 이게 그 서킷 뎁스가 깊어질수록 low 모멘트들은 first, second, third low 모멘트들은 아주 딥 서킷하고 똑같지만 하이 모멘트로 가면 달라진다는 거예요. 그러니까 이게 어떻게 보면 이렇게 테일이 왜 그 average는 peak로 결정이 되는데, peak 포지션으로 결정이 되는데, 테일이 달라져서 모양이 달라질 경우에 peak만 봐서는 알 수가 없고, average만 봐서 알 수가 없고, width만 봐서 알 수가 없고, higher moment를 봐야 알 수가 있는데, 이제 그런 네.
그리고 앞에서는 에로스테이트에 대해서만 이걸로 하는 것만 있으니까 여기서는 모든 스테이트, 모든 지베이스 스테이트를 다 이걸로 시스템.
그러니까 이게 어떤 스테이트가 우리는 생각할 때 어떤 스테이트를 누가 나한테 주면 그 스테이트의 어떤 캐릭터를 생각하는 방법이 얘를 지오 스테이트에서 얘가 되게 하려면 무슨 짓을 해야 됐을까? 얘가 어떻게 커서 여기까지 왔을까? 이렇게 보는 거예요. 그러면 이제 그때 스테이트 하나를 알 수가 있고 스테이트 알파가 있고 스테이트 베이타가 있으면 걔네들 각각이 지오 스테이트에서 어떻게 왔을까를 봄으로써 걔네들 둘이 얼마나 다른지를 보는 거죠. 그 트레젝토리 서킷들 사이의 차이를 보는 건데 그거를 이너 프로덕트 보지 않고 어떻게 보면 이제 길이를 보는 거예요. 근데 이런 그 모든 데 필요한 거리 이 서킷의 뎁스가 거리라는 매트릭을 주는 거예요. 뭔가 디스턴스를 얘기를 하려면 매트릭이 있어야 될 거 아니에요? 지으려면. 근데 이 서킷 뎁스가 그 매트릭을 제공을 해주는 거예요.
그럼 제로 스테이트 말고
그렇죠. 뭐든지 레퍼런스가 될 수 있죠. 아무거나 레퍼런스가 될 수가 있는데 그 reference를 쓰는 이유는 이거를 이렇게 theoretically 계산을 해서 bound를 주고 그러려면 뭔가 하나 reference를 잡아야 되니까, 그러니까 reference 하나를 잡으면 state alpha랑 state beta 사이의 distance라는 거를 state alpha를 reference에서 어떻게 됐는지 알고 beta를 어떻게 됐는지 알면 그걸 reverse 하면 돼요. 왜냐하면 unitary는 reverse 할 수가 있잖아요. 그러니까 unitary는 그냥 reverse 할 수가 있으니까 reverse 하면 alpha에서 alpha가 어떻게 갔는지 알았으니까 alpha에서 0로 다시 왔다가 0에서 다시 베타로 가는 거예요. 그러면 알파에서 베타로 가는 거리를 bound는 할 수가 있겠죠. 그게 최단 거리는 아니겠지만 항상 그렇게 재겠다라고 이제 결정을 하면 얘를 최단으로 잡고 얘를 최단으로 잡으면 이게 그 프레임 안에서 최단이 됩니다. 그러니까 이 컴플렉시티를 디파인을 하려면 그런 룰들을 정해야 돼요. 이런 식으로 재겠다. 룰을 정해놓고 그 안으로 재는 거예요. 네?
네, 그러면은 그 unitary evolution을 말씀하셨는데 unitary evolution이 아닌 일반적인 경우에는 적용이 되는지, 그러니까 제로에서 이제 알파, 베타 그런 다른 어떤 디스페이션이나 irreversibility가 들어오는 거. 좀 다른 생각을
오픈
해요.
시스템.
네.
그렇죠? 오픈 시스템이 되면 다른 문제가 되겠죠. 이렇게 디파인을 할 수가 없겠죠. 그러니까 이 데피니션에 여러 가지 문제가 있어요. 근데 오픈 시스템에는 디파인 할 수 없다는 것도 그들 문제들 중에 하나예요. 그러니까 우리는 처음에는 여기서 시작했지만 그거를 가지고 이런 서른한 디퍼런스를 데이터 파일이, 그러니까 진짜 우리 학생들이 일을 할 때 이제 데이터가 데이터 쉐어링이 되는데 폴더에 보면은 01, 01, 00000011 이런 스트링들이 밀리언 개가 있는 거예요. 그걸 이렇게 쳐다보고 있으면 잠이 와요. 여기 이 한쪽에 이렇게 쫙 있고 이쪽에 이렇게 스프레드시트에 있다고 생각을 해봐요. 000001 양쪽에 이렇게 쫙 있어. 이 순서도 랜덤하겠죠? 그거를 이렇게 눈으로 봤을 때 아무런 감이 안 온다고. 근데 그거를 그냥 에버리지 하면 다 0야. 양쪽 다. 에버리지는 다 0야. 그러니까 그거를 어떻게 구별을 할 거냐라는 거죠. 그런 데이터가 봤을 때. So the key thing about how we are going to learn this moment was to take the attention between the snapshots. So earlier, when we failed, we were attending within the snapshot. This is doing something funny. We were attending within the snapshot, which is to learn correlation in the space. That was spatial correlation. But once we started to think harder about what is it that we want to learn and how should we go after what we want to learn, we realized that we are really interested in temporal, the measurement to measurement fluctuation. And if that's what we're interested in, we should attend between the snapshots. Another thing that we realized was, so that's, I'll come back to another aspect of the structure. These are my collaborators. Haejin Kim is my graduate student. He's now in third year. Lee Ching-do is graduating. Lee Chen-ju is a postdoc. Kartik Barma is a former student. Yuri Lensky was a postdoc who really pioneered this work. Yuri is a special person. He's brilliant. He knew all this complexity theory stuff. I didn't know any of that. He came to me and said, this problem is very, very hard and very likely it will be even hard to machine learning. But if there is any way to try to learn this, it's not manually possible. So it will be interesting if we can try this, try to learn this relative complexity using machine learning. And he said, well, I don't know anything about machine learning, but it would be cool if we can work on this. And I knew a lot about machine learning, and because I've been doing this for 8 years, and I have kind of developed over the course of time how I approach problems and how I ask questions about the problem. So we started teaching each other, and that's how we got to work on this. And I think it was kind of helpful for me to not know how hard this problem was, because had I known, I might not have sort of dived into this head first. It was very hard, but eventually we succeeded. We had a great fun collaborating with experimentalists, Amir and Will Oliver at MIT. Jesse was doing intern at Google. and we collaborate my long and the order. So these architectures are designed for the sequence problem or the language problem. We needed to turn into architecture that respects the permutations. So understanding, if I want to solve a problem that's defined as a data problem, understanding the structure of my data is really important. Until we implemented the permutation symmetry, we were failing. Once we implemented the permutation symmetry, we started to succeed. So that was an important lesson. So then we used the architecture that respects the permutation symmetry, and we made it kind of economical because the computational cost can blow up. Attention mechanism is not cheap. So we designed the architecture so that we can take high order of movements or multiple self-attention layers without having to pay too much cost. And then eventually it has to come out to a single number, a decision. So this all of this data has to be compressed down. When we don't know anything better, what we do is, for instance, to average. That's one way of compressing everything, but I've said a number of times that's not a useful thing for this kind of problem, because all the averages are 0, or half in this case. So we need to find some other way of compressing, and that was learned. So that this was pulling attention block, and we added an additional feature where we can weigh different snapshots differently. And that was very helpful when we were working with noisy data of throughput, because noise occurs probabilistically, which means some sample is more noise than other samples. So if you learn to kind of discern what kind of sample, what a less noisy sample looks like, you can just put more weight on the less noisy sample and do well, even when you have a noisy collection. And that was the ability that was given to this decoder part. So this is the total architecture. Now, in remaining few minutes, let me just highlight what was learned for each of the 3 problems that we tried. First is to witness the entanglement transition. Skip this. With that. What is the problem? The problem here was hardcore boson in the strong repulsive interaction limit. So this is essentially a spin model problem that was implemented on their flip chip geometry, their flip chip and Will Oliver lab, 16 qubit problem. And as they increase the strength of this tuning delta by explicit calculation of subsystem tomography for different size subsystems and with the scaling, they found out that there is a small delta limit. Shows volume law that all the qubits form a very globally entangled, low-range entangled state. But when you increase delta, you go to an area loss state. So in an area loss state between 2 subsystems, entanglement is only just near the boundary, near the border. Volume loss states are hard to simulate classically because it's fully using that exponential. Area law states are easier to simulate classically. The volume law versus area law is an important thing to be able to distinguish, but the explicit rigorous definition of entanglement entropy is very expensive to obtain from data. You need multi-basis measurement, you need to do tomography, it just doesn't scale. So what we wanted to do was to use our quant. Let me just show you when it works. The quant 4 has 2 layers of self-attention block, which means 4 means it's going up to 4th moment, it's learning up to 4th moment. And the way we approached it is through supervised learning framework, where we train the machine with data from 0, delta over j equal to 0, which is a volume loss state, and delta over j equal to 2, which is the area loss state. When we don't use the attention mechanism, this is FNLP, same number of network parameters, that is from classical machine learning side, machine's complexity was the same number of parameters. However, the architecture was different, and without the attention, we just couldn't even train. we try to train saying that, look, this is a dog and this is a cat. It will say with a 50% chance it is a dog. It's not working. But once we use Quant, we were able to train, and you can see that the results get better and better as we make the set size larger. If the set size large, just by attending within the set, you can get a better sense of how the movements are changing. Next problem was the deep random circuit, complexity of deep random circuit. And this was work that Hedin started working on as a first year graduate student while I was on sabbatical leave. It's amazing that she got this working. It was a very, very hard project. It was a big collaboration. All the reasons for it to be really overwhelming for a first year graduate student. But she is really tough and she persevered with this. Really proud of that. The random circuit is this famous paper, Arut et al. This is a paper which declared Google achieving quantum supremacy. So what is this supremacy about? They said, okay, if we set up a random circuit of following a particular rule, consisting with various 2-qubit gates at each step, as you make the circuit deeper, in the ideal limit without noise, you will reach the this is a scrambling circuit. That is, scrambling means you are exploring the whole space of your Hilbert space. But as you quickly reach the exploration of the Hilbert space, you will be at a place where classical computing cannot map. So this plot, this is their money shot on that paper. Shows that their depth 20 would take to do an equivalent sampling that they can do with that 20 system for a classical computer would take 10,000 years. Now there are a lot of debates about whether this is really supreme. First of all, the experiment on hardware is noisy. So if you allow the classical computer to be also imperfect, that's only fair. Then it doesn't take 10,000 years. It can be done, I don't know what the latest record was, but it was definitely under a day, maybe 15 hours. But our quest was not whether the state is supreme or not. That's not my problem. My problem was the fact that the way they characterized the data was using classical computation. The XCD, cross-entropy benchmark, says if I get a measurement, zeros and ones, I look up what is the probability that particular measurement would occur given the knowledge of the full probability distribution. And I repeat that for multiple measurements. That's how you evaluate this cross-entropy benchmark. Cross-entropy benchmark compares what you have gotten from a known distribution. But how do you know this if you cannot get it exactly? They simulated the quantum circuit with classical computer, but they didn't have 10,000 years to simulate. So they simulated an approximate version of the exact circuit. And that's how this is evaluated. And what you're seeing is that this cross-entropy benchmark, which is a fidelity of how truthful is your data compared to your ideal distribution, is falling. It's falling because as you make the system deeper and deeper, it gets more and more dominated by noise. Every layer adds to noise. And what the challenge was to see whether we can learn how the states are evolving, the complexity is evolving with depth entirely from data. And that's what we want. And we're using the attention mechanism attending between the snapshots. So the approach was that, okay, give us data from shallow circuit and data from deep circuit. I talked about having a reference. Our reference in this case was the deepest circuit. So the circuit depth 20 was what we chose as a reference. That's the most scrambled state. And we are going to ask, okay, you circuit that this is a pile from some other depth. Can I tell the difference between this pile and the pile of that one? That's the way we look at it. So we spent about 6 months failing. So these are all the architectures that we tried that we failed. 50, I said 50% is random guess, it's failing. Once we started to use attention, we started to see. And that was really it was kind of, it happened around end of the year. It was very nice it was nice end of the year gift to us. Who is toiling in this problem. Now here, there's a contrast between these two. This is, this is looking at the second order correlation. This is the 50th order correlation. How do I know what is the order of correlation we're looking at? We know what is the architecture we use, how many times the self-attention was repeated. And from that, we can know that this is the upper bound of the moments that we were acting. So now we compare the cross-entropy benchmark result and with list data, simulated data. Cross-entropy benchmark reaches 1, which is what you would get in a deep depth limit. But at depth 8, from depth 8, you cannot distinguish. But Quan says that, yes, I can distinguish depth 8 from depth 20. So we're pushing the saturation bound to when we reach the full complexity, and we were able to extend the evolution, being able to tell apart the evolution. But more importantly, when we look at the experimental data, so this previous slide, this is simulated noiseless data. With the noiseless data from depth 8, XEV cross-entropy benchmark says I cannot distinguish between 20 and 8. Quan could distinguish between 8 and 20. But when we get to the experimental data, something more dramatic happens. Experimental data on XEV just says, okay, I'm getting worse and worse. I'm just deteriorate as I get deeper. Experimental data given to Quan trained on the noiseless data, although the noise is getting more severe as the depth goes, Quan was able to learn the features in the data that is evolving as the pure state was evolving. This is very much reminiscent of what we saw in the pure state that is after depth 1 and European. So this was exciting because from this very hard to learn subtle changes, we could undo the effect of the experimental. Final was to learn topological order from noisy data, which is to see whether we can decode. When you take the surface code without noise would have these loops, peak time from the loops of arbitrary size. That's what it means to be topological. That's what it means to be able to encode logical qubits. As you increase the order, these loops get broken, and you will lose the nature of the topological state, which gives the logical qubit definition. So how far can we tolerate the error is the notion of error threshold, and we were able to learn by having set size 64 that we can tolerate the incoherent bit split noise up to 0.11 and coherent noise up to 0.23. 24. These bounds for each node from mapping each axis of the problem to a random Ising model, but different models for each axis. So all of this intermediate regime were not known before. This was the first time without using the explicit mapping to a statistical mechanics model. A way of a procedure for learning the decodability was able to saturate the known challenge. This is sort of like how, and then we were able to interpret what the model learned, that it was learning to pay more attention. So it's paying more attention. So we look at all the snapshots, and because we have the attention score in the polling attention, we can see which ones got more attention by the machine in its precision compared to which ones got lower attention. So the snapshots got more attention had larger loops. When we look at the expectation value of the loop over the size of over the perimeter, they were showing the flatter distribution, like loops of all sizes were occurring for these samples that got more attention. And the machine learned to ignore the samples whose loop size is quickly diminished. So turned out these were samples that were more noise from the perspective of the distribution of the loop sizes, and these were samples that were less noisy. But we didn't tell the machine to evaluate the loop sizes and sort based on that. It just learned to do that because that's how it was able to get the right answer. So let me now summarize. I talked about quantum attention network, our machine learning architecture that uses attention mechanism to attend between the snapshots as a general purpose model for learning quantum complexity. Why do I say it is general purpose? These are all very, very different problems. And we are gaining confidence each time we apply this approach to different problems. This is a very effective way to learn the relative quantum complexity between different states. Coming back to the open system, right now we're working on learning measurement-induced phase transition. When you apply measurement to the system, then you are making the system open. It is no longer a unitary evolution, and things change in a very dramatic way. There is a notion of measurement-induced phase transition, which says when you measure below the certain measurement rate, you don't change the system as you don't entangle the system as much. So when you don't measure too frequently, because measurement affects the entire system, when you don't measure too frequently, when you measure gently and just infrequently, you remain in a volume law entangled state. When you measure frequently above certain threshold rate, you go to from area loss state to the volume loss state. Measurements can introduce entanglement across the whole system with everybody affected. So we are working on learning the measurement-induced phase transition, which is something that is occurring in the open system. The earlier rigorous notion of complexity wouldn't apply because it is not a unitary dynamics evolution. But Han still works remarkably, and we are able to learn measurement-induced phase transition without post-selection. If you know the subject area of measurement-induced phase transition. But if you don't, the point is this idea of attending between snapshots turns out to be a very productive way to study data from quantum simulators. So with that, let me finish. These are different problems that we looked at, and what we're working on now is leveraging the lessons that we've learned from this work to several problems we are working on. One is the measurement-induced phase transition. Another is working on developing decoders when you have error-corrected circuits or circuits with error correction, measuring syndromes, and you're applying logical gates with, for instance, transversal gates. When you apply logical gates, such as transversal gates affect the entire system. So if you want to do the error correction, you want to know whether the logical error occurred as you run the circuit. Deciding whether the logical error occurred is a decoding problem, and decoding problem has a binary outcome. Either the error occurred or it didn't occur. So it also fits very naturally into this kind of classification-based machine learning approach, and that's something that we're looking for. Thank you for your attention.
네, 질문 있으면 질문하셔도 되고요. 저희 항상 그렇지만 요 속 내용 질문하셔도 되고 뭐 다른 질문도 다 저희는 오픈해서 받습니다.
Thanks for the very interesting talk. I was wondering, you showed a distribution of attention. Now, will that kind of narrow down in the case of something that's near criticality?
In the distribution of the bit strings?
Yeah, or
the bit string distribution. Yeah, so the bit string distribution. What is that?
Or, I mean, there was like a distribution of attention that's kind of peaked.
Oh, you mean for the for the surface code? This.
Yeah, this.
Yeah. That's a good question. I don't know. Yeah.
So if it has like longer range correlations, I think if you take more snapshots of something.
Yeah, so here, so the left, this side is a little. So the left-hand side is, so this is a topological state. And this side is a trivial state. So what we do is we train with topological state, and we train on the two ends, data from the two ends, and then we give data from the middle. And when we gave topological state data, this was what the distribution of attention score, like how many snapshots got high attention versus low attention. And this was a distribution when we gave the trivial data. The machine distributes the attention. But what was changing between topological state and the trivial state was whether what it was paying attention to had the meaning that makes the distinction meaningful to us. So if you look at the state data that was deemed topological, the output was saying, okay, I think this is topological. For this state, the output was, no, I think it is trivial. If I look at the attention score distribution, both are distributed. But what was different was the states. When I look at the states that received more attention and compared it to the states that received less attention. In the topological state, looking at the Z loop length distribution, the loop length distribution. In the topological state, the data that were given more attention had the loop expectation value that's staying very robust up to large loop length. This is the notion of loop tension. The topological states are defined by saying in that wave function, you can have purely topological limit without any noise. When you take that wave function and make the Z loop expectation value, measure the Z operators around the loop. As you change the size of the loop, you are supposed to get exactly the same expectation value of 1. So in the ideal topological phase, irrespective of the length of the loop, I should get exactly the same expectation value. That's the topological phase. We call that vanishing loop tension. That you can have the loops of any size because there is no tension to make the loops larger. If in the trivial state, the loops of shorter length would have high sufficient expectation value because they are more related. But it's not topological anymore. There isn't a sort of global entanglement. So expectation value would drop as I look at larger loops. Okay. Now the machine, we didn't tell this to machine. We didn't tell it to look for loop expectation value as a way of distinguishing topological state from the trivial state. But when it was given the ability to distribute attention, and when it was told to look for the distinction between this type of state to this type of state, it learned to pay more attention to the data that has the loop expectation value that does not decay significantly as a way of learning what is a topological state. Now, to this attention, which is not distinct from the Z loop expectation value point of view, right, for this trivial state, why it was putting more attention to this set versus that we don't know because we didn't look. But what we can confirm is that it was learning the topological state in a way that is consistent with how we would have looked for this as humans from theory point of view. Whether this is the only thing that it was looking, we also don't know, right? The model is complicated a bit, but at least this much of learning is something that we would approve. this is what we would have wanted to do anyway if we could do it manually. So that kind of made us feel, gave us confidence that this is something, doing something right. Any other questions? Can ask me.
여기 간단한 것만 두 개
네.
여쭤보겠습니다. 그 QA에는 한글 용어를 어떻게 사용하고 계시는지, 어텐션이라는 걸 내가 번역을 한다면 어떻게 사용하고 계시는지 하나하고, 혹시 이 중에 유니터리 펀드에 대해서 좀 알고 계신지 있으면 설명을 좀 해주시죠.
한글 용어로는 아직 생각을 안 해봐서 모르겠어요.
어텐션에 어떤 어감을 집어서 만약에 번역을 해야 될까요?
저의 전문 영역을 넘어서
예.
제가 답을 못하겠습니다. 번역이 있어요. 저는 유니터리
펀드에 대해서 제가 최근에 알게 됐는데 혹시 거기에 대해서 알고 계신지.
유니터리 뭐에 들었나?
펀드.
유니터리 펀드 그것도 제 전문 영역이 아니래요. 펀드가 저의 전문.
또 세미나 감사합니다. 제가 이걸 제대로 이해를 했으면은, 마치 고양이하고 개를 이렇게 구별하듯이, 인텐그먼트 스테이트라고 아닌 거를 구별하는 거라든지, 토폴로지컬이나 아니면 트리기어를 구별하는 것에 대해서, 퀀텀 영역에서 적용하는 된다. 이거는 이제 생각하는 것 같은데, 그러면 이게 실용적인 면에서 예를 들어서 이번에 클래시컬 컴퓨터를 사용한 것보다 더 대화 고양이를 비슷이 잘할 수 있는데 적용이 가능한지.
네. 좋은 질문이신데요. 그러니까 보통 이제 그게 그런 퀀텀하고 머신러닝이 같이 오면 그런 질문, 그런 퀘스트를 할 수가 있죠. 퀀텀 하드웨어를 써서 머신러닝을 하면 클래시컬 컴퓨터로 우리가 쓸 수 있는 컴퓨터로 하는 것보다 더 잘할 수 있는가. 그런 예는 아직 없어요. 네.
발전해서 그런
네.
게 하나 질문하면 요즘 얘기 나오는 게 엔비디아 GPU를 쓰면은 무슨 이건 팬텀적인 거를 뭐 제너레이티브 AI나 이런 거 인해서 굉장히 할 수 있다고 설명을 막 했는데, 그런 게 그러면은 도입되면 이제 이런 퀀텀 영역에 특수적인 면으로 가능한 건데.
그러니까 엔비디아는 이제 여러 가지 비즈니스에서 이 퀀텀 그런 umbrella 안에서 다른 프랙티스를 하고 있는데, 어떤 회사들은 퀀텀 하드웨어를 만드는 데 투자를 하고 있고, 엔비디아가 투자하는 건 뭐냐면 이제 엔비디아의 하드웨어는 클래시컬 같은 하드웨어인데, 우리가 클래시컬 컴퓨터로 퀀텀 시스템을 제일 잘 시뮬레이트를 하겠다. 그러니까 가령 뭐 예를 들어 서킷들이 클래시컬 서킷만 쓰면 클래시컬 컴퓨터로 많이 시뮬레이트를 할 수가 있어요. 클래시컬만 써도 한없이 많이 할 수 있는 건 아니지만 그래도 좀 많이 할 수 있어요. 이제 그럼 남들은 어떤 비즈니스들은 IBM이랑은 퀀텀 컴퓨터를 만드는데 너는 왜 클래시컬 컴퓨터를 푸시하느냐. 근데 그게 의미가 있는 게 퀀텀 컴퓨터들은 다 노이즈가 있고 지금 아직 에러 커렉션이 보급이 안 된 상태고 이제 막 에러 커렉션 하는 게 의미가 좀 있지도 않을까라고 하는 상태거든요. 이제 브레이크 이븐 포인트를 이제 막 터치하고 있기 때문에 왜냐하면 에러 커렉션을 하려면 실제로 메저먼트를 해야 돼요. 메저먼트를 계속 봐야지 내가 에러가 생겼나? 생기면 고치고. 근데 생겼는지를 보려면 계속 메저먼트를 해야 되는데, 메저먼트를 하면서 스테이트를 인터뷰를 랩삽할 수가 있거든요. 그러니까 메저먼트를 해서 에러를 크랙하고 큐비트를 더 많이 써야 되고, 그다음에 에러 커렉션 하려면 그러면 이제 큐비트를 많이 써서 늘어났을 때 에러도 더 많이 늘어나고, 메저먼트를 할 때도 에러가 늘어나고, 그러면 그거를 할 만한 값어치가 있어지는 게 이제 브레이크 이븐 포인트인데, 브레이크 이븐 포인트를 이제 겨우 터치했다고 얘기를 하고 있어요. 몇몇 그룹에서. 그렇기 때문에 아직 에어 프레션이 안 되고 있는 상태에서는 하드웨어들의 노이즈가 많이 있고 그 노이즈를 나름대로 모델링을 하지만 그거를 정확하게 알 수는 없어요. 어디서 어떻게 보인다고. 그렇기 때문에 이 퀀텀 컴퓨팅을 하는 그룹들이 모두 다 그 이제 퀀텀 컴퓨팅을 뭘 하면 패러럴하게 클래시컬 컴퓨터를 시뮬레이션 해요. 최대한. 그러니까 그 시뮬레이션에 대한 니드가 이제 점점 더 상당히 많이 늘어난다는 거죠. 그래서 엔비디아의 비즈니스 그 아이디어는 비즈니스 모델은 다들 퀀텀 컴퓨터들을 만드는데 모두 다 그 벤치마킹을 하려면 클래시컬 컴퓨터로 그 똑같은 서킷을 최대한 많이 시뮬레이트를 해야 될 거기 때문에 우리가 그거를 잘할 수 있는 환경을 만들겠다. 그게 엔비디아 많이 푸시하고 있어요.
또 질문. 예.
네.
네, 그 좋은 말씀 감사합니다. 그 지금 보여주신 결과는 주로 이제 슈퍼컨덕팅 서킷 관련 데이터인데 혹시 이제 다른 커넥티비티를 가진 다른 이제 그 플랫폼에서 좀 차이가 날지 그때는 이 어텐션 아키텍처가 좀 달라질 수 있어요. 이런 부분을 좀 보여주세요.
지금 보여드린 일이 그 이제 어드벌 그룹이라고 한 거랑 구글이라고 한 거가 다 이제 클래스만 베이스 시스템인데 그것들을 한 이유는 그 데이터를 저희가 콜라보레이션을 해서 할 수 있었기 때문에 그렇고 이 아키텍처 상에서는 스냅샷을 그냥 주면 할 수가 있어요. 근데 이제 머신러닝을 하려면 스냅샷 3개, 4개 가지고는 안 되고 50개 가지고도 안 되고 100개도 좀 적고 10개쯤은 돼야 뭐 좀 해볼 수가 있거든요. 우리도 이렇게 셋으로 나누니까 10개를 주면 100개짜리 셋으로 10개를 만들어서 이제 할 수가 있다는 거예요. 아까 셋 사이즈가 너무 작으면 반에서 그래서 메저먼트가 한 1000개 정도는 나올 수가 있어야 돼요. 그러면 그것만 되면 플랫폼하고 사실 상관이 없어요. 근데 저희가 이제 처음에 이거를 해본 문제 제일 처음에 시작을 한 게 그 구글의 페드럼 러션이 코넬에 와서 세미나를 했는데 그게 2021년 2월인가 그때 와서 이제 세미나를 하면서 그때 이제 저는 그때 처음 배우기 시작했어요. 이런 문제들에 대해서 그러면서 그때 챌린지를 하더라고요. 이그 스프리머시 그 실험 데이터를 가지고 우리가 두면 이게 딥이 샬로인지 너네 구별을 해낼 수 있겠느냐. 또 챌린지를 하면은 동해가지고 버벅 덜컥 무식하니까 버벅 덜컥 뭐 그랬더니 이게 어려운 거. 그래서 이제 그렇게 시작을 해가지고 이렇게 됐는데 지금 그 measurement in space transition은 measurement를 해야 되는데 mid-circuit measurement가 어렵잖아요. 이 트랜스먼으로는 mid-circuit measurement 하기가 어려워요. 그래서 이게 근데 그럼에도 불구하고 구글에서 그 MIT 페이퍼들을 여러 개를 냈죠. 낸 거에서 그 결정적이었던 거는 mid-circuit으로 안 하고 그거를 끝에 가서 한 번만 하게 그 타임 스페이스 듀얼리티를 써서 여기서 김현이가 똑똑한 사람이라 구글한테 정말 필요한 아이디어를 줬어요. 걔네는 믹서킷을 못하니까. 그래서 믹서킷으로 게이트를 할 수 있는데 메저먼트는 시간이 그래서 구글 페이퍼들은 그 믹서킷 메저먼트를 안 쓰고 메저먼트 뭔가 끝에 가서 쓰는 그렇게 MIT 페이퍼들을 썼는데 사실은 믹서킷 메저먼트를 하기에는 정말로 믹서킷 메저먼트를 하겠다. 그러면 그거를 하기에는 다른 플랫폼들이 더 나아요. 가령 아이언 그 트랩드 아이언이 믹서킷 메저먼트 하기에는 더 나은 플랫폼. 그래서 지금 그 MIPT 일을 하고 있는데 그거는 그 이제 우리는 지금 아직은 시뮬레이트 해가지고 머신러닝 하고 있는데 그 페이퍼는 이론이랑 시뮬레이션을 가지고 페이퍼를 낼 거지만 그걸 어디에다가 임플리멘트를 한다고 하면 현재 생각으로는 트랩 다이언 시스템이 제일 유리하지 않을까 그렇게 생각을 하고 있어요. 그래서 저희는 이제 이런 문제들을 생각할 때 그 데이터를 잘 내려고 노력하시는 분들이 많이 있으니까 우리는 누가 주는 데이터를 갖다가 그걸로 뭘 해보자. 그렇게 접근을 하기 때문에 어떻게 그 데이터가 만들어졌는지는 사실 애그노스틱해요. 그리고 이 머신러닝을 써서 디코딩을 하겠다는 것도 그게 의미가 있다고 생각을 하는 이유가 보통 현재 디코딩 스킨들은 모두 그 노이즈 모델을 써요. 그러니까 그게 어떻게 하냐면 이런 어떤 퓨어 스테이트가 있을 때 거기에 이렇게 노이즈 모델을 써서 그럼 이제 이게 나왔어. 그거랑 실제 데이터를 구별을 해서 리버스 엔지니어링을 하려고 하는 거거든요. 그러니까 포워드 모델을 해서 비교를 한 다음에 포워드 모델 한 거를 비교를 해보니까 얘네들이 똑같아. 그러면 노이즈가 이렇게 돼서 이렇게 러지컬 에러가 생겼거나 안 생긴 거야. 근데 그 포워드 모델을 해야 되기 때문에 그러려면은 그 노이즈 모델이 필요하거든요. 근데 그 노이즈 모델을 이제 우리가 생각을 했다는 거죠. 가우시안 그런 것도 생각할 수 있는 거야. 한정이 돼 있으니까. 근데 우리가 이렇게 그 데이터를 실험 데이터를 가지고 노이즈 모델 그 머신러닝을 해서 에러 아니면은 시뮬레이션을 해서 이렇게 에러가 생긴 거 안 생긴 거를 이렇게 해서 디코더를 만들면 그 데이터 안에 들어있는 노이즈 모델을 머신이 배우는 건데 그거를 우리한테 이렇게 알려주진 않겠지만 이게 지가 알아서 배우니까 우리가 모델링하는 거에 그 한정적인 뷰를 벗어날 수 있다. 그래서 노이즈 모델, agnostic 노이즈 모델을 상관없이 할 수 있다. 대신에 이제 데이터의 리딩을 필요로 합니다.
네, 또 질문.
아까 이런 건 능력들을 그거 생각이 있어요. 그한 잘했던
아니요. 예. 그러니까 그 스테이트를 구하는 거 너무 어렵다고 그랬잖아요. 그래서 그 스테이트 토모그래피를 안 해요. 토모그래피를 안 하고 그냥 네가 이만큼 잘 컸으니까 알아서 배워봐. 그럼 그게 왜 될 수가 있냐면 Z-based measurement에 될 수 있는 이유가 이게 그냥 보통 Z-based measurement를 쓰면 하나하나만 보면 Z-based measurement 하나만 보면 거기에서 퀀텀 메커니컬한 다이내믹한 인포메이션을 알 수가 없어요. 근데 이게 그 Z-based 스냅샷 두 개 사이에 코릴레이션을 보잖아요. 그러면 지금 이제 이 큐빗을 봤을 때 이 스냅샷이랑 이 스냅샷을 비교해 보면 얘는 업이었는데 얘가 다운이 됐어요. 그러면 여기랑 여기 사이에는 x가 업그레이드 한 거죠. 업에서 다운이 왔으니까. 그리고 얘는 다운이었는데 업이 됐어요. 그러니까 얘랑 얘 사이에도 x가 업그레이드 한 거죠. 그래서 이거랑 이거를 같이 보고 비교를 함으로써 x measurement의 이 사이트 이 큐빗의 x measurement와 이 큐빗의 x measurement 사이의 correlation을 볼 수가 있는 거예요. 그래서 x measurement의 correlation을 볼 수 있으면 사실 entanglement 그 스케일링이 바뀌는 거를 알 수가 있거든요. 왜냐하면 entanglement 엔트로피는 log of rho니까 non-linear한 quantity긴 한데 그 density matrix 보통 이제 어떤 observable을 measure 할 때는 expectation value를 measure 하면 trace of row times observable이잖아요. 그러면 row가 이제 density matrix인데 근데 그 entanglement 엔트로피는 log of row란 말이에요. log니까 non-linear 하잖아요. 근데 entanglement 그 transition을 quadratic order만 가도 좀 배울 수가 있어요. 볼 수가 있어요. linear order에서는 전혀 볼 수가 없지만 quadratic order만 가도 density matrix의 quadratic order만 가도 entanglement transition을 디텍트를 할 수가 있어요. 그거 이제 theoretically 알려져 있었거든요. 그러니까 x correlation을 본다는 거는 그 density matrix의 quadratic order에서 볼 수 있는 거기 때문에 그거를 볼 수 있게 만들어 보니까 얘가 디텍트를 할 수 있었던 거 같아요. 그렇게 생각합니다. 네.
추천님 데이터 그런 굉장히 들어오는 정보를 구하는데 자기 혼자 또 정보를 헬스가 있는 거지. 네, 실제로 이 퀄리티 컴퓨터에서는 기본에 있는 새로운 정보를 범하는 만들어내는 이제 데이터 스토리지가 있어서 그런 장점이 있기 때문에 혹시 그런 거
그러니까 제너레이팅 모델링을 할 수 있느냐는 거죠. 네. 정말로 들어보니까 제너레이팅 모델링. 네. 데이터를 만들어내는 거.
생성형.
생성. 근데 이제 할 수 있죠. 그러니까 그 프로버빌리티 디스트리뷰션을 배우면 그걸 모델을 하면 그 다음에 이제 데이터를 만들 수 있어요. 그러면 이제 그 프로버빌리티 디스트리뷰션을 정확하게 배우는 거 알아내는 거 어렵다고 했잖아요. 정확하게 알아내지 못한 상태에서 만드는 데이터는 정확하지 않겠죠. 그러니까 내가 그 probability distribution을 좀 적당하게 배웠어. 그리고 뭘 만들었어. 그러면 그렇게 해서 만들어진 데이터가 실제 probability distribution에서 만들어질 수 있는 데이터랑 똑같지는 않을 거야. 확률이 다르니까. 내가 모델할 수 있는 거에 한계가 있으니까. 그렇지만 뭐 비슷하겠죠? 비슷할 수는 있겠죠? 정도껏 비슷하겠죠? 그러니까 그거는 내가 얼마나 많은 데이터를 넣어서 얼마나 정밀하게 이걸 모델링을 했느냐에 따라서 그 데이터가 얼마나 진짜 같으냐가 달라지겠죠. 근데 이제 그런 식으로 해서 그 데이터 양을 줄이고 적은 데이터로도 뭘 해보겠다. 그런 연구를 하는 분들이 있어요. 그런 연구들도 보고 있어요. 근데 이제 저는 제 개인적으로는 아주 개인적으로는 이제 어떻게 보면은 페이크 데이터를 만드는 거잖아요. 그래서 조금 저는 안 하려고. 네. 그렇게 해서 밸류를 만들 수 있는지 아직 저는 모르겠어요.
네, 또 질문. 아까 서글 질문 연장 선생의 일러 아이트를 한다 그러면 서켓 width는 그러니까 큐빅 개수는 어느 정도 있으면 좀 일을 재밌게 하겠어요. 5개 이보다 어려울 거잖아요. 그렇죠?
그러니까
50개 있으면 좋은데 아이트를 이제 50개 모시면
50개
없으니까
네,
그러니까 그렇죠?
50개까지는
하여튼 5개는 아니고
네, 5개는 너무 적고
예, 어느 정도
열 몇 개?
열 몇 개?
네,
20개 미만이어도 좀 의미가
50는 안 넘어갔고
예.
50까지는 안 가고 지금 그거를 일을 하고 있는데 이제 무슨 트랜지션을 얘기하려면
그렇죠.
트랜지션 얘기하고 이제 그러면은 또 이론하는 사람들이 좋아하는 거
그렇죠. 그런 거
그런 거 하려고 하면
그
파이널 세이 스케일링을 해야 되는데 그러려면 이제 여러 사이즈가 있어야 되는 거예요. 근데 기본적으로 저희가 지금 생각하는 그 로우 행잉 프루트는 트랜지션이 있다는 거를 포스트 셀렉션 안 하고 클래시컬 시뮬레이션 안 하고 보여주자. 그러면 이제 그거를 보여주려면 뭔가 이렇게 트랜지션 같으려면 그 트렌드가 우리가 그 메저먼트 레이트를 바꿀 때 트렌드가 리니어하지는 않아야 되겠죠. 리니어하면 그냥 이렇게 익스트라폴레이트 하는 거니까. 그래서 그러면 이게 이렇게 약간 밴드하는 것 같이 보이려면 그러니까 이제 실험을 하시는 분들은 그 데이터를 많이 구하기가 어렵잖아요. 알트rop은 그러니까 그래서 지금 지난주에는 이제 그 샘플 컴플렉시티 스터디를 좀 했어요. 그 몇 개 정도 스냅샷이 있어야 이게 이렇게 안 보이고 그래도 이렇게 좀 피는 것처럼 보입니다. 그랬더니 700개면은 이렇게 괜찮게 보인다고. 시스템 사이즈는 큐빅 한 열 몇 개 정도에서 10개에서 한 20개가 그 레인지.
하나만 더 드리는데 몇 번째 한 번.
저는 대학에서 나와서
네.
학기는 양자정보연구지원센터 스킬을 활용해서 시험 개발에 도 관심이 있으신지 아니면 주변 커뮤니티에
그런 연구를 하십니다.
신약 개발을 하려면 신약 개발에 제일 가까운 거는 고등학교 과학 교과서로 따지면 화학이겠죠. 그러니까 이제 뭐냐면은 신약 개발 방향으로 가려면 화학 문제를 풀 수 있어야 되는 거잖아요. 저는 이런 응용 쪽을 잘 모르는데 사실은 뭐 퀀텀 시뮬레이터도 공부를 한 지 얼마 안 돼요. 한 3, 4년밖에 안 됐어요. 근데 이제 그러면은 제가 생각하는 건 그러니까 신약을 구체적으로 생각해 본 적은 하나도 없지만 제가 많이 생각을 하는 거는 이 퀀텀 시뮬레이터들로 퀀텀 컴퓨터로 어떻게 하면 밸류를 만들 수 있을 것인가. 뭔가 달리는 하기 어려운 거, 뭔가 이렇게 의미가 있는 거, 가치를 창조를 돈이 많이 들어갔으니까 뭔가 나오는 게 있어야 될 거 아니에요. 그런 거는 생각을 많이 해요. 근데 그럼 이제 그게 가치가 창조될 수 있는 방향이 클래시컬하기에는 정말 어려운 게 사실은 다이내믹스거든요. 그러면 이제 다이내믹스 언제 필요하냐? 타임 에볼루션을 봐야 이제 뭐 프리퀀시를 안다든가 그런 거. 그러면은 스펙트로스코피를 모델했을 스펙트로스코피를 쟀는데 실험으로 뭐 NMR을 하든지 그 스펙트로스코피를 인버스해서 그걸 써서 그 모lecular structure를 이해할 수 있으면 뭐 제가 듣기로는 잘은 모르지만 상당히 작은 모lecule들도 그 이제 스트럭처에 따라서 몸 안에서 하는 기능이 많이 달라질 때 그 스트럭처를 알기가 어려운 경우가 많다고 하더라고요. 그래서 이제 그런 게 좀 의미가 있을 것 같은데 제가 화학을 모르기 때문에 화학을 모르기 때문에 저 혼자는 못하고 이제 화학을 잘 아시는 분이랑 해야 되겠죠.
교수님 오시고 저는 진짜 2시간 중에 한번 양자정보가 있어서 또 활용하고 있습니다.
저는 이론을 하는 사람이라서 제 연구실에는 스크린만 있어요. 근데 저는 다른 실험하는 사람들하고 제 연구실에는 컴퓨터도 없어요. lap탑을 들고 다니고. 근데 저는 이제 다른 실험하는 분들하고 일을 많이 해요. 그래서 뭐 IBM하고도 일을 하고 구글하고도 일을 하고 뭐 실험하시는 분들하고 하버드에 계시는 분들, MIT에 계시는 실험하시는 분들하고 일을 많이 해요. 저는 실험을 못하고 저는 이제 실험하시는 분들이 고생해서 데이터를 얻으시면 그거를 존경심을 갖고 열심히 꼼꼼하게 들여다보고
실험하시는 분 얘기가 나왔어요. 그런데 구글 머신은 이렇게 콜라보레이티브를 봤으니까 자사람들을 모르는데 그 하드웨어를 만들고 있는 사람 입장에서 구글 머신의 예를 2019년 처음에 그 퀀텀 스쿠터에서 시카모하고 지금 시카모는 사실 굉장히 엄청나게 잘 많이 발전된 머신이거든요. 하드웨어 면에서는. 근데 이제 정말 이론하는 유저 입장에서 볼 때
차이가 나죠.
차이를 느끼실 수 있으세요?
그럼요.
IT 있으세요?
네.
그러면은 하드웨어 하는 사람들이 몸을 갈아 넣은 게 보람이 있을 거고요.
그렇죠.
왜냐면 이게 하드웨어 하는 사람들 입장에서는 굉장히 몸을 갈아 넣어서 조금 좋아져서 한 3년 전, 4년 전 들어보면 지금 머신은 그때 머신하고보다 훨씬 좋은데 과연 그걸 써서 이렇게 예를 들어 어플리케이션 하는 사람들이 그걸 느끼고 있는가에 대한 질문은 좀 있어요, 사실. 왜냐면 그게 조금
그러니까 어플리케이션이라고 하기는 어렵고
어떻게 뭐
데이터를
예.
그 머신에
데이터를
나오는
보시잖아요.
데이터를 보는 사람 입장에서
네.
그 노이즈 레벨이
네.
훨씬 줄어들었죠.
그걸 보실 수 있어요.
그럼요.
네.
그 보이죠.
그럼 그게 유용성이 있을까요? 그만큼 그러니까 스터디하는 데는 도움이 돼서 뭐 유용성은 떠나서 그 전에는 못 보던 걸 좀 보는 거.
아까 그 랜덤 서킷,
예.
랜덤 서킷의 퓨어 스테이트 에볼루션을 노이즈 데이터에서 보고 싶을 때, 그 노이즈가 웬만큼 있으면은 그게 노이즈가 있어도 좀 그 밑에 있는 트렌드를 보려고 할 수가 있는데 노이즈가 완전히 너미네이트 해버리면은 못 보잖아요. 뭐 그런 차이가 있는 거예요. 그리고 뭐 가령 이제 디코딩을 하려고 한다. 그러면 이제 우리는 머신러닝 디코더를 개발을 하는데 실험에서 나오는 데이터가 모두 다 디코딩 할 수 있는 threshold보다 높아서 할 수가 없으면 나는 그 두 개의 트랜지션을 보려고 하는데, 그러니까 안 좋은 데이터만 가지고는 트랜지션을 얘기할 수도 없고, 얼마만큼까지 노이즈를 터널레이트 할 수 있는지를 보려면 노이즈가 적은 거가 데이터가 있어야 되니까 그런 부분이 있고, 기본적으로 그 하드웨어, 그리고 뭐 오늘은 얘기를 안 했지만 최근에 IBM하고 한 일은 그 피보나치 애니온이라고 그런 이제 그 애니온을 컴퓨터를 만들면 그거를 그 그라운드 스테이트를 그 스테이트를 그 웨이브 펑션을 잘 샘플링을 하면 어떤 그래프에 관련되는 그 폴리노미얼을 이베리에이트 할 수가 있어요. 근데 그게 이제 샘플링을 하는 거거든요. 그러면 그게 노이즈가 없으면 요 몇 개의 스테이트는 이런 앰플리튜드가 나오고 다른 애들은 앰플리튜드가 안 나오고 뭐 이제 그래야 돼요. 그래야지 그걸 가지고 이베리에이트를 할 수가 있는데 이게 circuit depth가 150 그렇게 가면 이게 이제 리밋인 거예요. 그 IBM하고 일할 때 여러 군데 머신을 썼거든요. 근데 결국 나중에 그 퍼블리케이션 퀄리티 데이터를 내려면 제일 IBM 것 중에서 제일 좋은 머신을 써야 됐어요. 그거 줄 서서 기다려서 익스터널 유저는 못 써요. 근데 그거를 이제 그 IBM 리서처들하고 콜라보레이트를 하니까, 근데 그 사람들도 아무 때나 쓸 수 있는 게 아니더라고요. 줄 서서 큐를 넣고 기다려서 쓰더라고요. 그러니까 그 제일 좋은 거가 이게 뭐 100몇 큐빅짜리였는데
133.
내 이름은 기억이 안 나. 무슨 새야?
헤론.
헤론인 것 같아요. 맞아요. 헤론이었던 것 같아요. 근데 이게 큐빅이 그렇게 많아도 그거를 다 쓰는 우리는 정말 퀄리티가 좋아야 되거든요. 그러니까 그 많은 것 중에서 제일 착한 애를 찾아야 돼. 제일 착한 애들은 또 그 근방에 있어야지 같이 뭘 해야 되니까 2큐빅 게이트를 해야 되니까 제일 착한 애들이 이렇게 좀 모여 있는 데를 찾아서 걔네들 몇 개를 쓴 거예요. 9개. 100개가 있다고 주면 그 문제에서는 100개보다 정말 퀄리티가 좋은 애 9개가 필요해요. 그러니까 개수로 경쟁이 안 되더라도 퀄리티로 경쟁이 되면 재밌는 일을 할 수가 있거든요. 근데 그때는 이제 IBM 머신들 여러 개 있는 중에서 제일 퀄리티가 좋은 애를 찾아서 그 안에서도 그 칩 안에서도 제일 퀄리티가 좋은 큐빅들을 찾아서 걔네들 이렇게 데리고 한 거예요. 노력하시는 보람이.
자, 마지막 질문 하나만 받겠습니다. 혹시 있으면. 없으면 여기서 정말 열정적으로 강의해 주신 김은하 교수님께 다시 한번 감사드립니다.